Now that we've introduced the unit circle and talked about measuring angles on the circle, I'd like to discuss how we can evaluate trigonometric ratios, namely sine and cosine, using the unit circle. Let's go back first to a geometry definition. If we're looking at an angle theta on a right triangle, sine of theta measures the ratio of the opposite leg to the hypotenuse. Cosine of theta measures the ratio of the adjacent leg to the hypotenuse. So we say sine of theta equals O over H, cosine of theta equals A over H, where each of these is a length. These will always result in output values with an absolute value of 1 or less because the hypotenuse H is always larger than the numerator, the opposite leg or the adjacent leg. Now what does this look like on the unit circle? I want to imagine drawing an angle theta on the unit circle. It corresponds with some point x, y that lies on the circle. Now the unit circle has a radius of 1. And if I want to measure cosine of theta and sine of theta using the unit circle, this triangle, I'm going to say cosine of theta is the adjacent leg over the hypotenuse, so it's x over 1, which is just equal to x. And sine of theta is the opposite leg over the hypotenuse, so it's y over 1, which is just equivalent to y. So we see that on the unit circle, cosine of theta is the x value, and sine of theta is the y value for this point, x and y, that's associated with theta. Sometimes this point is called the terminal point that corresponds to the angle. I want to emphasize here that when we talk about cosine of theta and sine of theta, we are thinking of these values as functions of theta. They have an input of an angle measure that may be in radians or degrees, and they have the output of a real number within the range of -1 to +1. So I want to see how we could find some of these terminal points, these x and y values for different angles. I'd like to discuss first finding the x and y value for a 45-degree angle. Let's use a little bit of geometry here. So we want to know what is this x value and what is this y value. We're looking at a 45-degree angle, and if I drop a leg down, I've made a right triangle here on the unit circle. This angle must also be 45 degrees. And we're using a geometry fact that because the two angle measures are the same, we're looking at a 45, 45, 90 triangle. The x value equals the y value here. The legs of the triangle are the same. So x equals y for whatever these x and y values are. Now let's use the fact that on the unit circle, x squared plus y squared equals 1. And because x equals y, we can make a substitution here. We can say x squared plus x squared equals 1, or 2x squared equals 1, which means x squared equals 1/2. We'll take a square root to evaluate for x, so square root of each side. I'm only going to consider a positive square root because the x value must be positive. We're working with a length in the first quadrant here. And I get x equals the square root of 1/2. We could rewrite this as 1 over root 2, and we could rationalize this denominator by multiplying by root 2 and rewrite it as root 2 over 2. So for a 45-degree angle, the x value is root 2 over 2 and the y value is root 2 over 2. xy equals root 2 over 2, root 2 over 2. And of course that means if we wanted to evaluate cosine of 45 and sine of 45 degrees, we would say cosine of 45 degrees equals the x value, which is root 2 over 2. Sine of 45 degrees equals the y value, which is also root 2 over 2. Sine and cosine of a 45-degree angle are the same. So in a similar way, using some creative geometry, we could find the x and y points for a 30-degree angle, for a 60-degree angle, and so on. I'm not going to show all of that here, but I'd like to look at a finished sketch of some of the special points on the unit circle. Here I'm looking at some angles from 0 to 90 degrees in the first quadrant of the unit circle. And looking at this sketch, I can now evaluate the sine and cosine of any of these angles. Let's say I want the sine of 0 degrees. Remember, that's the y value. And as I look at the terminal point associated with 0 degrees, the y value is 0. So we say that sine of 0 equals 0. Or maybe we want sine of pi over 2. Pi over 2 radians is the same as degree measure. If you're more comfortable with converting to degree measure, you can make that conversion first. Sine of 90 degrees, again, is the y value of the point at 90 degrees, and the y value of that point is equal to 1. So sine of pi over 2 equals 1. Cosine of 45 degrees was one that we evaluated above. That's the x value at 45 degrees, which is equal to root 2 over 2. And finally, sine of pi over 3. Pi over 3 is 60 degrees. And because this is the sine measurement, that's the y value at 60 degrees. Here is the point that we're looking at, and the y value is root 3 over 2. So we can begin to use the unit circle and some of these terminal points to evaluate sine and cosine of many of our angles.